In this lecture, we are going to discuss about the types of transmission lines. The first type of transmission line is the strip line. Now, talking in detail about strip line, first, how a strip line looks. This is a figure representing how a strip line looks. W indicates the width of the conductor. Basically, a strip line is a conductor sandwiched by an dielectric in between two ground planes. These are the two ground planes, and this is dielectric, and this is the conductor. Conductor we are talking about. W is the width of the conductor, T is the thickness of the conductor, and H is the distance between the ground planes. Now, there are other variants of the strip line. Here, the conductor is exactly in between the two ground planes. We have two other variants of strip line also. These two variants are suspended strip line and offset strip line. Offset strip line is, it is not exactly in between. Actually, this is like this, which is almost half a distance from here and here. But in an offset strip line, it is not exactly half. It is somewhere here or here. In suspended strip line, this distance is not half. That is, either it is up or down. Coming to the advantages and disadvantages of strip line. First thing is, strip line is a TEM transmission line media, and this is a TEM transmission line media. That is, it supports pure TEM wave. That is, the radiations come like this, and they bounce back because there is a ground plane here. And this is non-dispersive. What is dispersion? At different frequencies, if there is different behavior, then it is said to be dispersive. That is a kind of disadvantage because there is kind of fading in that variant. But this is non-dispersive, so this is an advantage. And the strip line filters offer better bandwidth than microwave counterparts. That is, if a similar component, a similar functionality is implemented in a microstrip line, then this strip line offers more bandwidth. What is the importance of offering more bandwidth is, more the bandwidth, the signal can propagate through that channel without attenuation. If the bandwidth is less, the other part of it is attenuated. So now the next advantage is, it has no lower cutoff frequency like the waveguide. And coming to the disadvantages, the fabrication of this is little bit tougher than the microstrip line, and for a given impedance, the strip widths will be narrower. That is because you have a second ground plane also here. You will notice why this is said to be a disadvantage compared to the microstrip line. Now this is the equation for calculating the impedance. 60 by epsilon r log of 4h by 0.67 pi w, 0.8 plus t by d. T is thickness, w is width, epsilon r is permittivity, relative permittivity. Actually, you have terms called relative permittivity and effective permittivity. For normal strip line and offset strip line, for suspended strip line, both of them are equal. But for the other variant, both are not equal. So, if effective, you have to calculate effective permittivity again. And now coming to the microstrip line. This is almost similar to the strip line, but the upper ground plane is not there. If the upper ground plane is placed, then this also can be called a strip line. This is a planar transmission line, and this is dispersive. I already said strip line is non-dispersive, and this doesn't support TEM wave because the waves, if they come like this, because there is no ground plane, there is no actual TEM wave that exists. It is only quasi-TEM wave that exists in microstrip line. And coming to the components, because the conductive strip is exposed outside and there is no, there is no extra ground plane on the top. This conductive plane is exposed. So the components can be easily placed onto it, but disadvantage comes when we require shielding, that is high isolation requirements. The shielding is not proper here, whereas it is nice in strip line. And the calculation of this effective permittivity. There are two cases for this, where considering the width of the strip and distance between the strip and the ground plane. H is the distance between strip and the ground plane, W is the width of the strip. If that ratio is less than 1, we go for this equation, calculating the effective permittivity. Epsilon R is relative permittivity. The same is with W by H greater than 1. The same two cases exist when we come to the calculation of Z0, that is impedance. Now we have already discussed about strip line and microstrip line. We have something called fin line. Fin line is very much similar to the slot line. This is something, this is very similar to slot line, but it is bounded in a rectangular waveguide. This solves the problem of installation of diodes into a rectangular waveguide. This figure shows how a fin line is. This is similar to a slot line. This is a slot that exists between. W is the width of the slot, epsilon R is relative permittivity, H is this. And it is usually suited for millimeter applications. It consists of partially metallized dielectric substrate shielded by rectangular metal enclosure. This is the metal enclosure. And the Z0, the impedance that can be realized here is in the range of 10 to 400 ohms. And the dominant mode here is the hybrid mode. The substrates that are used are RT duroid, Kevlar and Kapton.